Hello. In this lecture, we will review a few efficient techniques to deal with polynomials. You should know what a polynomial is, and this definition should be familiar. The coefficients can be over an arbitrary field or a ring, but when they are over the complex numbers, which includes the real, rational, and integers, the fundamental theorem of the algebra guarantees that this polynomial has n roots, not necessarily distinct, and we can write it like that. You rarely see a problem in the test that tells you to explicitly solve a polynomial, but this situation arises in a lot of problems, whether it is a characteristic polynomial of a matrix or the solution to an optimization problem. You have to know how to deal with those roots efficiently. Usually, you need to find roots or prove the lack thereof. You sometimes need to conclude irreducibility of a polynomial, meaning that it cannot be factored into two polynomials of lesser degrees. We will deal with that in the advanced module. Our tools are inspection, which is a fancy word for guessing. By guessing one root, we can reduce the degree of the polynomial, making the next guess easier. We have a theorem to help us find all the rational roots, and vieta to help us prove that a number is not a root or to do a sanity check. We will mention Eisenstein in the advanced module. So, how do we find the roots? For degree less or equal to 2, there is not a problem. But what happens if we have something like that? The first guess should always be plus and minus 1. It works more times than not. Now, we need to find the rest of the roots, and we will do that by dividing the original polynomial by this one. Doing long division on polynomials is something that you should know how to do. Try to take a minute and work it out yourself. There's really nothing to it, it is just technical. So, we can find the rest of the roots by inspecting P2. Let's use the following theorem. Given a polynomial with integer coefficients, make sure that they are, then if a polynomial has a rational root of the form r over q, r must divide the free coefficient, and q must divide an. Good. Now, how to use it? We just need to write down all the possibilities of r and q. In this case, r divides 12, so we have 0, plus and minus 1, 2, 3, 4, 6, and 12. And for q, only plus and minus 1. How convenient. Every r over q combination can be a root, but when checking, don't repeat the signs. 2 over 1 is the same as minus 2 over minus 1. After finding one root, we can reduce to quadratic polynomial, and then we are done. We will do that in a minute, but for now, this is a good spot to mention vieta. Note that his formula works regardless of the field from which the coefficients are taken. Observe the formula for the sum of the roots and the product of all roots. Immediately, we see that 0 is a root if and only if the free coefficient is 0. To see if 0 is a root is very easy and should be the first root candidate to consider along with plus and minus 1. Now, I would advise you to stop the video and work out the rest of the example. So the roots are 2, minus 2, and 3. The theorem should have given you one of those three roots, and then the best thing to do is reduce the degree of the polynomial again. This is another example that you should work out for yourself. Note that we don't have integer coefficients here, so we cannot use the theorem, or at least not immediately. Please solve this example before continuing. So the coefficients are not integers, big deal. The roots don't change if we multiply by a constant, right? So multiply by 2 and then we can use the theorem. Find one root and reduce the degree. Notice that 1 has multiplicity of 2, so technically using only the previous theorem is not enough. It does not tell us anything about multiplicities. But we have this theorem. The multiplicity of z is k if and only if it is a root of the polynomial, of course, and it is a root of all the first k minus 1 derivatives, and it is not a root of the kth derivative. Quiz. As usual, this is an exam-like question. This style of questions repeats itself. You are given 3 statements. Each can be true or false. You must choose A, B, C, D, or E based on the instructions, which can be which of the following are true or which of the following are false. Here, for example, if you find 2 and 3 to be true and 1 to be false, choose E as your answer. Alternatively, if you found all the statements are true, you should check yourself because this is not one of the possible answers. Take a minute and a half to solve this. Stop the video now. Okay, ready for the answer? It is B. Here I wrote P, derivative of P, and P multiplied by 2. The theorem of the rational roots applied on 2P eliminates statement 1. Applying it on P prime eliminates 3, so 2 must be true since none of the above is not a given possibility. But one can check that 2 over 3 is indeed a root of the derivative of P denoted as P prime.